Okay. Again, many thanks to you for the kind invitation and introduction. Yes, I am a physicist, so as a atomic and nuclear physicist, completely new to this topic. But we observed the electricity production situation in Germany that is quite astonishing, as Richard Wagner, sorry,
thank you.
Friedrich Wagner.
He's dead already.
Friedrich was already told. And our question was, why is it that way? And so we are looking for a quantity that's of a reason why it is so. And if we look to many publications concerning energy economy, we saw the quantity EROI, and when looking at the many publications, we saw large variances of that value. And we again asked why. So the topic here is to solve the solution by giving information of our publication. It is that here. You can find it. You can't find it on the server now, but we will provide it soon. And I will concentrate on methodology because I will give some numbers or many numbers, and if you want to discuss this, of course, more numbers. But the point is, I can say it to that at very first, the large variance is minor to data variance, but major to methodology variance. So I will concentrate on the methodology we used, contrary to the methodology others used. So now I come straight to the motivation. The problem now, the question we want to solve is the influence of the power generation systems. What is the influence of the power generation systems on the national economy? And then we want to compare them. There are two things. We want some invariant description, and we want comparability, so consistency. And as a physicist, we see that in the EROI as a physical quantity, especially the term energy is a physical quantity by definition. So the EROI is a quite nice quantity for that question because it's like an amplifier for the societal economy. It is something a power plant technique emits to the society that can be used, and on the other way around, the society has to invest for that. Okay, but now the difference, now the special. To remain physical, we use exergy amounts. I come to that later, real exergy amounts used, but the point here is that the exergy, that is the part of energy that is able to do usable work from thermodynamics, it's a key word here, because if you look at the society, what drives economics? If you have a amount of oil, maybe inside the earth, it has no value for you because it lies there and you do nothing with it. But if you want to heat your home or drive your car, somebody has to extract it, somebody has to deliver it, and so on. So make it usable for you. And the bill you pay is not some kind of energy content of that oil. You pay the work of the supplier. So that's why we see the exergy as the main, the key here for our analysis. Okay, to fit the EROI for our purposes, again, comparability and consistency, the EROI should be invariant against non-physical issues. I come to that later, what this means. So we stay strictly on the terms energy or exergy in that case. And uniformity is important because that's for comparability, that we treat all techniques the same way. So questions like environmental standards, safety standards should be included. That can, of course, be considered and should be considered as physical countermeasures against pollution or against other things. And that leads us to the methodology we used. Okay, again, we try to use strict exergy contents. So for the output, it's easy. We use only the electricity output. The heat is ignored for that. And that has the advantage that also techniques that only emits exergy, wind, solar, PV, and so on, are completely comparable to others. And exergy, of course, itself has the advantage that it is versatile in usage. Also heating, if you like. Think of France, that is heating with nuclear electrical power. The next thing is the output, the electricity output, should not be weighted as done in several other publications. But for our purpose, and for to remain consistent here and physical here, it is no EROI in a physical manner. If you weight it, then you have some kind of fossil fuel replacement factor, but no relevant societal economics here in terms of exergy. So the input weighting is more complicated. The input should not be weighted for the purpose that we come closer to the exergy approach. Of course, this masks the comparability. I come to that later for the issues. But if you have the data available and available to the public and transparent, that is a minor problem because all the others can check and reproduce or alter the scenario, and of course can add new data. Okay, we have published our raw data. This is a Google table linked from the paper. Here you see the link again. And that fulfills the transparency criterion to an extent. So we listed there the exergy input as far as it is known. And of course, there are many fractions of energy input that are where the exergy contribution is not known. This is the task for the future.
Excuse me, you use the word should.
What?
You use the word should. Should not be included or should be included or whatever. And
in terms of a consistent physical approach, as I defined it before, I see from the prior, things. Think of social EROI or money-related EROIs and so on. This will answer a different question. We want physical efficiency, and then we have a margin for the society to exploit that. And this margin can be used, for example, for some kind of friction, if you like. Let it say psychological effects, or as you like. We want to stay invariant against arbitrary conditions. We just want to say what is the efficient, the technically most efficient solution for the question. Okay. So we have to continue with our constraints. To be realistic, to reflect the current state of the society, the current society's technology, we have to determine the exergy flows, especially for the input, this is the point, that are really used, not theoretical ones that can be obtained by the chemical or physical process. That is not the point. That is really used. There should be databases available that contain such exergies, but it is by far not sufficient. So another important point is found in several studies. There are also EROI definitions that include the fuel energy content into the input. That means the EROI for a conventional power plant is always smaller than 1, and for renewable it is by definition greater than 1. Because another point is, then I told before, the output is weighted with a factor of 3, and now the input for the fossils contain the fuel energy content. So there's no point, no physical reason why doing that. Because the society never touched in any way the fuel energy content. Humans don't put energy into the fuel carriers. They just extract it or refine it, something like, or transport it. So if you take a power plant, maybe coal, you have a large amount of extracted fuel carrier energy, and the needs for building and maintaining the power plant is negligible compared to that energy content. So you have just fuel carrier electricity out divided by fuel carrier energy in. This is the thermal efficiency of a power plant. That says nothing about the economic efficiency, physical-economic efficiency. Now I come back to the non-physical efforts. The other inputs like labor or interest and so on are ignored for this study. This is because of 2 reasons. We have a non-physical part in labor, for example, and we have a physical part. That is true. The physical part, there are exergy contributions in labor and so on, but they are smaller than the overall energy consumption, for example, of labor, and we don't know them from databases. For me, it is not known that there's any database available that shows labor exergy efforts just to operate a power plant or build a power plant or something like that. The completeness is important because now we have to include all inputs that are regarded to the power plant. So operation, deconstruction, construction, fuel supply, and so on. Some studies forget that. And the recycling is one thing. This is a minor thing, but it's important. Some studies, especially for renewables, say subtract the materials completely that are recycled, ignoring that the recycling itself needs energy. So better is use actual data from material inventories, and there the recycling process is included already. Okay, now I come to the system borders. You can see such an area. This is the analyzed system, so the power plant together with the so-called helper facility. What does that mean? To a power plant, there is immediately necessary such a facility because for the fossils and nuclear, you need to extract the fuel, and for the renewables, you need to storage. What has that in common with each other? The storage for the fossils is the fuel. So we just need to extract it, but we don't need buffering in any way. For the renewables, we need the storage systems because no fuel carrier is needed. On the other way, we have several other inputs invested by the society, but from outside of that system. Yes, mining, not mining efforts, but supporting industry that builds and maintains the power plant and constructs that helper facility. The output, of course, is the gain for society. Now there is only one question left. The following problem. Imagine pump operation on site by electricity that is generated by the power plant itself. So the pump is the element of the power plant. You have two possibilities to evaluate this for EROI. You can subtract it from the output or add it to the input. So what is, what makes sense here? You have to put a border to distinguish between the two methods. So from the so-called investor's point of view, the investor sitting here in the power plant, you can say, okay, I paid for the device exergetically, and now the exergy used by this pump is the exergy I generate myself. So the second method would be intuitive to use, because now I subtract it like a kind of friction or efficiency loss. If, for example, nuclear power plant is shut down, no power generation, this pump must be keeping running for cooling issues and so on. But then the electricity is fed from the outside grid. So then method one would be the more intuitive method. We use that way.
Can you show the arrows that are E in 1 and E in 2?
Sorry?
The arrows that correspond to E in 1 and E in 2 that you have at the denominator.
Okay, this is only abstract. We divided the complete inputs in these two components, just for the purpose that we have E in 2 as the example for the pump operation. It doesn't matter where it is shown here. It is just for methodology.
Or if you draw the boundaries, as I think you have, and the pump is internal to it, then you don't need to deal with it because E out is out of the system, out of the analyzed system, and E in is energy from somewhere else that goes into the system.
Yes, in that case, yes. And for the example given, if the power plant is online and feeds its pump itself, then this electricity amount doesn't leave the system. That's okay.
So could we just simply say E in 2 is power output stays inside the white box?
Even closer, it stays inside this area.
Yeah.
Yeah? In the second case, not. It comes from the outside. Okay. So now we have the methodology, but we have some issues we have to consider. The first, and I think the most important, I mentioned it before, is the comparability that would be hampered if we don't weight the inputs. But as I said, we want to get close to our approach and take countermeasures in form of transparency. So everybody is invited to look at the data and make his own scenarios and add data. So the second point is, and that points to the energy carrier fuel has to be input issue. The resource range is often the cause for that, because LCA says resource flows through the society should be monitored, but we have a very different approach. The physical approach says exergy flows because this is dominant for the to run the societal economy. So the fuel content does not reflect the physical EROI anymore. So for the fuel scope, that means just the extraction expenses should be considered, and these depend only on scarcity. So if you have a power plant running for a time where the ore concentration remains roughly the same, you can make a static model as we did and consider the actual ore concentration. So that is included in our work. The other non-physical, yes, sorry, sure.
I don't want to interrupt you, but okay. Can we go back one slide?
Just one.
Just one. You're using the term power plant,
Yeah.
which is confusing to me, and when a power plant I think of as a thermal plant or something like that.
It's a thermodynamical machine. Thermal plant is, think of a wind turbine. It's a thermodynamical machine, but is it a thermal plant by your thoughts?
I'm thinking of getting oil, okay? And so, for getting oil, or wind, but we're getting oil, where's the fuel in this diagram?
What do we want? So,
Raw material industry?
Coal mining is in the helper facility.
what is your problem? I don't understand you.
It says coal mining in helper facility.
No, I understand that, but okay, I'm getting confused by a thermal plant, in which case you're calculating efficiency of the plant. When I say EROI, I say EROI is for an energy extraction process. And is your power plant an energy extraction process?
Okay, maybe I should make points clear. I need a system that inevitably emits electricity, exergy. This could only be done by a thermodynamic machine. Wind turbines, together with the sun, can be seen as a thermodynamical machine. So, this is the power plant. And then I need the exergy inputs, not fuel carriers or something like that. I need the exergy flows that came from different sources. I have to consider all, of course. So, what is missing in your... so the fuel...
Getting coal out of the ground.
Yes, this is an exergy need. Mechanics, for example. You are right, of course, because of insufficient data, we have non-exergy energy data on top of it. But this is my... I will come to it later. This should be resolved by additional data.
But I'm going to be concerned, personally worried about it, not because I think you're wrong, I don't know, but because I'm not really understanding how you think about EROI.
Okay.
Okay, now go ahead, and hopefully you'll explain it to my satisfaction.
Imagine you have all the data you need. all the data. Then you can extract the mechanical work and the electrical work that is needed. This is, only this should be considered ideally for the input.
Okay.
Lifting concrete, making concrete, because this also needs exergy and so on. Every process in thermodynamics that lowers entropy uses exergy. That's the point, because an economy that should be wealthy in a physical manner needs exergy to lower its entropy. And so every process done here.
I have no problem with that. I agree with you completely on that. I'm just trying to conceptualize how you're thinking about.
Maybe we should discuss it at the end. Is it okay? Yeah? Okay. Okay, again to the non-physical inputs. So labor, interest, and so on, in a very detailed way by Pedro and analyzed for photovoltaics. These inputs are to a main component non-physical inputs. They have exergy components, of course, that should be considered. Again, we ignored them because we don't know them, but they are minor contributors to our calculation. In the monetary economy, they are relevant, they are more relevant, but money means something more than only energy. There is a relation between money and energy, but this relation is not constant. It is a bit arbitrary because of non-physical issues. So we discarded them in our analysis. So using a reasonable planned load and respective lifetime and maintenance is an issue in many publications that was not consistently used. We give them for a defined location, Germany, and the EROI depends then only on that location and on the actual industrial technology, because we have to include real used exergy flows. But against every other societal issues, the EROI is then invariant. Now to the results. Okay. This is also, yes, this is a diagram published in our work. So if we have here the renewables, and here fossil, nuclear, and hydro, and as you can see, for every technique we have two results, the unbuffered and the buffered result. So again, we take storage into account. We use the cheapest possibility to be conservative, although it is known, thanks to Friedrich Wagner, that it is not applicable in Germany to the extent. We refer to a work from Matthias Popp et al., to make things easier for us. He analyzed in detail a European and German scenario where storage is calculated in full load days to be stored for 1 year. And he gets for a German scenario 20 to 30 days. This fits very well to your 8% or 7%. But we are conservative. We make a mixture between a European scenario and German. We take only 10 full load days. But even then, you see that the EROIs buffered for techniques that have to be buffered lowers considerably. Here we have for solar photovoltaic 1,000 full load hours and 25 years lifetime, about 4 unbuffered, 1.6 buffered. Okay, biomass fed as a gas fed into combined combustion gas turbine is 3.5. It's not buffered. For wind, it is from 16 to 4. Solar CSP is a quite optimized calculation because again, insufficient data. So we have low storage amounts because it's a location in Morocco desert. We assume 2 days storage, so the drop is not that large. Then we have the fossils. This is coal. A brown coal is a bit lower than hard coal, but around about 30. For natural gas from a combined combustion gas turbine, it's 28. Here we have a renewable that is quite efficient, and that is only a medium-sized 90 megawatt facility, 35 buffered, because buffering for hydro is much more predictable. And now we see nuclear, 75. Okay, I will come to nuclear later, but now a comparison. I take some values here. I hope it is okay when I say Prieto in that case, because you analyzed it yesterday. And in my calculation, roughly you obtain 2.5 roundabout. Yeah? Okay, and there's another value bigger than 20, and unbuffered we obtain roundabout 4. Okay, so if we take 4 and adjust it to the Spain location in Spain, for example, because here is 1,000 full hours, you have 1,700. The performance factor is included here, so in your study. So I multiplied, it came to 7, 6 to 7. This is 2 to 3 times higher than yours. So why it is lower? Because you have amount of data used and so on, reasonable methodology, but there is one difference. You use labor, the labor and something else, taxes and so on. Mostly. And that is the difference of the methodology, physical versus more economical value. And now we can point to the value by Raugai. He calls it an EROI PE, primary energy equivalent. That's the weighting of the output I mentioned. Yes, he called it, you can see it in the publications. So he says electrical output 3 times or 1 divided by the efficiency of an average fossil plant park. Then you get, yes, 3 times the value, not 7, 6 or something, but 20. Okay, that's but this value says nothing in that manner we analyze here. So again, for nuclear, we have 2 publications with rather low values. Why that? This is not peer reviewed, this is some kind of website or website report. Very, very detailed, so we can see it. The first point is he uses very old data. He imagines diffusion from the 70s. He takes into account high extraction efforts extrapolated on lower mine concentrations than proven today. And then he came to an energy input just for extraction for a mine located maybe in Africa that is 3 times as high that the whole country consumes. Now, this is obviously nonsense. And the second point is he makes a top-down analysis. So he takes into account very high, let's say high monetary investments converted to energy. And then he gets on top very, very high inputs that has nothing in common with physics. So then it is reasonable that we have a factor 2. And the top, and this is even topped by Tyner, and he gets only a factor of 1. Okay, and then I come to that, to the quantities to the differences. So, fossil fuels. Fossil fuels. we include the primary energy, the heating of the fossil fuels, in an input that we have not done, but this is an issue that I've not shown because this makes the thermal efficiency. The second point is we have weighting when the energy quality is weighting. Okay, for output and input, this gives a factor 1.5 to 2. Then the recycling issue gives up to 1.5. The conventional plants often are top-down analyzed. So we have a factor up to 10. And so on. So if you sort this for renewables and conventional plants, you have a variance of factor 20 to 50. And that explains the huge variance. Okay, then I will make a detailed example for nuclear, or more detailed example for nuclear. This is taken from our publication. So we analyzed a German power plant. As the data source, we used a non-peer-reviewed source, but we compared it with peer-reviewed sources where either material inventories, energy inventories are given, or material amounts are given. So this is consistent. So the output is clear. The 60 years is a reasonable lifetime. The US proved it. And so, so we have that output. These are the inputs. We gave the electrical contribution, and as you can see, the far biggest part is the fuel-related input. And that leads. So these are two different values because this is enrichment 17%. Sorry.
That's separating the isotopes mostly.
Yes, that is main. This is the main contribution in that value. This is 17% diffusion, the rest centrifuge, and here completely centrifuge. So you have an EROI of 75 or and 105, just switching to pure gas centrifuge enrichment. Nothing else. So now, what is a good EROI? 75 was the highest value we obtained in our comparison, but is it a good EROI? As a physicist, I say no. So look here. These are the relations in the fuel carriers. Of course, the 100 million is unfair because the ore concentrations are maybe a factor of 1,000 less, but you should definitely have more than 2.5. So what is the reason? Okay, this is in German. I'm sorry. I will explain it to you. This is a nuclear power plant, and here you have the components outside the plant that contribute to the energy input. You have the extraction. This gets more and more important today because the enrichment, still important, gets less important because of significantly more efficient enrichment. Diffusion takes about 100,000 kilowatt hours per kilogram reactor fuel. Centrifuge just need 2,000, 1/50 of that value. So this is quite a difference. So okay, this is ignored. Then you have the disposal, and you have where is it? Yeah, there should be a facility that prepares the rods, of course. Ah, yeah. Okay, so we have together just for the fractions. We have mining now is the most important because there can be a scarcity evolution be observed. Then enrichment, then to equal parts construction and disposal and operation. And now again, the evolution of the EROI. Although the scarcity works against nuclear, it rises because of technology exploitation, in that case of enrichment. This is a number for the plant gas laser enrichment, the SILEX process, that has to be commissioned as a prototype in the US. Sorry?
Daniel, I see that you put there uranium mining, uranium conversion and enrichment. In the previous page, where is it? I don't see what the previous one. The previous one. Not the previous one. When you calculate all this, no,
Oh, sorry. Sorry. Here? Here? Do you mean? Okay. These are fuel-related costs. That includes mining plus enrichment, of course. But as you can see here in the difference, enrichment, at least here, was the main contributor. Less here. Then mining comes more important. But overall, oh, it's a bit slow. Ah, yes. But overall, the EROI is raising. Okay, but what can we do? We can give a solution because we don't only criticize. We want to make solutions. So our institute develops a kind of the reactor design. I will make things short. This is a fast breeder reactor, so we can use all fuels. This is very compact. You just imagine that, I mentioned it yesterday, you reduce the fuel extraction amount to 1%, just because of the better usage. That's one point. So if we make steps, the enrichment process I explained before, construction and operation, the construction of the power plant is significantly less, but because of the remaining inputs, it's not so significant change here. But now, the uranium supply, which is the main contributor, or was, for the light water reactor, is down to 1%. So we have a dramatically increase in the EROI. The same methods, nothing changed. The fuel cycle, all the facilities around can be omitted because this power plant, maybe somebody heard of the molten salt reactor that makes online processing of the fuel. Just by simple processing, we just make distillation processes. So this is by far not so complicated like classical PUEX processes. So this gives another gain of a factor 2.5. So we are getting at full exploitation, of course, EROIs in the range more than 1,000. Magnitude in the order of magnitude relatively close to that limit. Again, here the numbers that we published in our work. Okay, I will make a short summary because we have a to-do list. So, I make the important points. Never use the fuel inventories for a physical EROI. Use state-of-the-art technologies and be consistent in your condition and constraints. For example, location dependency that could not be avoided. And if you summarize studies, have a look on the study if the study methodology fits your own methodology to answer your question that you have to EROI. So, and this is the main point. You should add more information, not you itself, but we should gain more data for the inventories to extract exergy contents or electricity mechanical to simply get the contributions of each energy quality. So to summarize, in that point of view, for pure economic efficiency in a physical way, the most saving potentials are the usage of efficient power plant technologies. That's the summary. So, and I may say it, I'm from Germany, avoid using inefficient technologies. So that's what I want to say. Thank you very much for your attention.